Okay, number 19, we actually did this one in class, and it says, so I'll go quickly here. The length of human pregnancies is approximately normal with a mean of 266, standard deviation of 16. Probability that a randomly selected pregnancy lasts less than 260 days. That's this area here. This is my normal calculation. So probability that x is less than 260. You can find the z-score or do normal CDF. And you get the minimum, negative 999, a really big small number, 260, and then the mean and standard deviation. And if you do that, you get 35.2%. So I got a 35.2% chance of an individual woman having a pregnancy less than 260 days. B, suppose a random sample of 20. Describe the sampling distribution. Well, if n is 20, since the population is normal, this will be approximately normal. So mu sub x bar is going to be 266. Sigma sub x bar is 16 divided by the square root of 20. Okay. Now C. What's probably the random sample of 20 is less than 260. Okay, so probability that x bar is less than or equal to 260 or less than. It's the same way either way. That's this area. So we're going to do that the same as the up above, normal CDF, except the standard deviation is the only thing that will change. So if you do that, you will get 4.7%. So a much smaller chance of getting an average of 20 less than 260 than getting 1 less than 260. D. Probably the random sample of 50. Okay, so I'm just going to change this to a 50, and that would be probability of x bar is less than 260, and this is for n equal 50. So again, it's normal CDF, and I'm going to do the same thing, except the standard deviation way over here is now 16 divided by the square root of 50. So if you do that, you get that percent. So it's going to be move the decimal over 2, so it's going to be 0.4%, less than 1%. What might you conclude if a random sample of 50 pregnancies resulted in a mean gestation period? Well, I would say, and I'd be really surprised, because something that happens 0.4% of the time happening is a shocker. So I'm either going to say it's a bad sample, but it says it's a random sample. Okay, so if it's a good sample, and I really got this, 0.4%, I really got this sample, and that has a 0.4% chance of happening. My estimate is that this 266 is really a little bit smaller. In other words, that the 260 is not so far away from the mean. Okay. And F, what's probably the random sample size 15? We'll have it within 10 days of the mean. Okay. So mu sub x bar is 266. Sigma sub x bar is 16 over the square root of 15. And within 10, each way, is going to go from 256 to 276. So the probability that x bar, that x bar is between 276 and 256. And if you do that, you will get 0.9844 or 98.4%. Okay, because this is a small standard deviation, so reality is it's way out here to way out here. Okay, and 26. Time spent in the drive-through. Oh, we did this one in class also. I tried to pick problems that we didn't do, but so we're in the drive-through, and it tells us the mean is 59.3. Standard deviation is 13.1, and it's skewed to the right. That's the population standard deviation. Then it says B, to obtain probabilities regarding a sample mean using the normal model, what sample size must be required? Well, if I want the sampling distribution to be approximately normal, then I've got this is mu sigma sub x bar must be sigma over square root of n. Then that happens is normal, or actually approximately normal, if n is greater than or equal to 30. Okay, so that's that. Quality control manual, which is using a new delivery system designed to get cars through the drive-through. Random sample of 40 cars. So if n equals 40, it says the mean time x bar is 56.8. Okay, so we're looking at this. Oops. This is 59.3. That's the population. Standard deviation is 13.1 divided by the square root of 40, and 56.8 is down here somewhere. So what's the probability of obtaining that or less? Probability of x bar is less than or equal to 56.8. So you do normal CDF over here. I'll write it down. Or you can find the z-score and look it up on the table. Negative 999, 56.8, 59.3, and 13.1 over the square root of 40. And if you do that, you get 11.3 minutes or seconds, I guess. And the question is, do you think that the new system is effective? Well, the average time went down from the mean time. I mean, the population mean was 59, this is 56. But the chance of that happening randomly to get a wait time less than 56.8, somewhere in this to the left of 56.8, the probability of that happening, oh, I said 11 seconds, I'm sorry, percent. Is 11%. So the probability of me getting a sample less than 56 is 11%. That could have happened by chance. Okay, and C, the next 50 cars, simple random sample. There's a 15% chance the mean time will be at or below what value? Oh, okay. So now what we're doing is we're saying this. Here's my distribution. Mu sub x bar is 59.3. Sigma sub x bar is 13.1 over square root of 50. And they're saying there's a 15% chance the mean time will be at or below what value? So I don't know what this value is. I'm going to call it, what? Not x. Let's call it a bar, or no, y bar. Okay, because these are averages, so I can call it y bar. And this is 15%. So I want to go backwards and figure out what y bar is. So that's inverse normal. The area to the left, the mean, and the standard deviation. And if you do that, you come up with 54.7, and that is seconds. All right, there you have it.